continuing education hours. We are continuing that, so we fund the activity, and it is approved by AORN, and I am an Ethicon employee. So this is worth 1.0 contact hours of continuing education credit. At the end, I will provide a website as well as a course code for you to go out and get a certificate. And we were passing around a sign-in sheet, so please make sure that you fill that out as well. So what we're going to talk about today is the basics of electrosurgery. How come I say electrosurgery? Why don't I say the basics of cautery or the basics of electrocautery? Can anyone describe the differences of those three terms to me? Because I'm going to bet you have electrocautery, and I know you have electrosurgery devices in your operating room. You're probably not using cautery. Those were Civil War methods. But what are the differences? Cautery. What's cautery? It's branding iron, right? I put a branding iron in the fire. It heats up, I achieve an effect. That's how they achieved hemostasis a long, long time ago, right? You take a rock, heat it up, and it causes a burn, right? What's electrocautery? You all have electrocautery devices in your house. I said branding iron. What's an example of an electrocautery instrument in your house? How about just a regular iron or a curling iron? I plug something in that uses electricity to heat up an element. Your toaster is an electrocautery device. If you're toasting bagels or bread in your home, you're using electricity to cause heat into elements that causes an effect on what it is that you're doing. Electrosurgery is actually using electricity itself, where the patient has electricity typically passing through it to achieve a tissue effect. And those are the big differences. So some semantics, but I think they're important because the terms are very, very different. And the proper term for what we're talking about today and why we're going all these safety considerations is because we do use electricity with the patient, okay? So let's take a look at what we're going to talk about today. These are our objectives. We have 7 of them. Describe the significance of a completed electric circuit, the difference between the types of generators that you may have had in your operating room at any time, compare the different types of dispersive electrodes. These are what we would call return pads or grounding pads, and I'll tell you why the proper term also is return pad. Discuss the various waveforms, including the advanced forms of energy we're using in the operating room today, comparing monopolar and bipolar technologies, the purpose of active electrodes, and then finally some patient safety considerations. So just a quick survey. They surveyed our urology surgical team, and some pretty startling statistics. Nearly half hadn't had any training regarding the use of electrosurgery, and 64% had no formal energy-based training as well. And then 49% could only answer some very basic questions. So let's talk about the significance of the circuit. Based on that picture, when was the first operation done using a electrosurgical pencil?
53.
53? Anyone else? 1926. Everybody familiar with the name Bovie? The Bovie was invented by William Bovie. Surprise, right? Branding stronger than Kleenex. Do we still call it a Bovie today? Right? But I want you to look at that problem that they fixed. 90% mortality in neurosurgery. Neurosurgeon has 10 patients. He has to tell 9 of them probably they're going to die. Instrument like this radically changed that. I want you to think about what you do every day, whether it's a knee, a hip, maybe CV, and not having this instrument. How much clamp cut tying would you be doing, and how long would those procedures take? What would the hemorrhage be like? It radically changed what we did. And the safety, more importantly, the safety of everything has evolved over time as well. Electricity is incredibly lazy. It takes the path of what?
Least.
exactly, least resistance. What's happening here? Why does lightning do this? It's taking the path of least resistance. It's got to complete its pathway, it's got to complete its circuit, and when it is branching off, like we see it branching off in this photo, it is taking the path of least resistance. This is a basic overview of how electrosurgery works. We take 60 cycles out of the wall and we convert it to over 400,000 cycles per second. That is a critical thing. For that reason, that is why patients don't get electrocuted when we use these instruments. We're operating now at an electrical circuit that is higher than the neuromuscular pathway. It's a very important thing, and we'll talk in a minute why. But the main job is to take energy at a high current density at the tip of this blade and disperse it over a wider area here. That's why this has surface area. Current concentration here, dispersing it on a pad here. And we'll talk about these pads shortly. We've had two types of generators. Anyone seen a ground reference generator? We shouldn't see them anymore. I think they still get used. They probably get used overseas. But these were the original generators. A big problem. We call it a grounding pad because of this concept. These generators were grounded to the floor. So if you did come in contact or something like that, you got some shock. Now, we talked about this converting electricity out of the wall from 60 cycles to 400,000 cycles. We take the ground out of this and put it here, which is a huge safety improvement. So we call these now isolated generators. The ground's not taking place in the wall anymore. It's taking place here. And the proper name for these are actually return pads, not grounding pads, because we're returning the electricity back to this generator, which is essentially a transformer. That's what's happening here. It is transforming the electric current and how it works. But a big safety improvement because you had alternate site burns and other issues regarding a lot of things with those generators. Let's take a look at the patient return electrodes. There's typically been three types over the year. The first, single foil, literally one sheet. What you should all be using now, do you still use these? I should ask that first. You think you use these? Okay, so we'll talk about that. Dual foil, this is the standard, what should be here. And then finally we have what are called capacitive pads. Single foils, we really shouldn't be using. Again, the dual foil pad is a considerable safety improvement. What's happening here? What's this photo? Is that an arm? Or is that a hip? It's a hip. So what's happening there? What happens with these single foil pads is, do these sometimes fall off or get dislodged in surgical procedures? Probably. I know in my time I've seen that happen. So where this is one surface area, again, high current concentration at an active electrode, we want to disperse it over this area. When it starts to peel up, am I getting rid of that surface area? I am. It's a big problem. So when this starts to peel, is this green? Absolutely is, right? Is it attached to anything? So this can be a big problem. And let's demonstrate that. Ryan, can you be my expert demonstrator? I promise not to electrocute you. Okay. Actually,
Yeah.
Sure. Hold the pad. Actually, let's see. There we go. turn it up. Everybody see what's happening there? I have very minimal contact and it's starting to smoke. See that? Can everybody see the electricity? So this is the problem with single foil pads. We're using the whole surface area, but it's not smart enough to know that it has minimal contact. So I don't know if you can see it, but there's, see the sparking? The arcing that's happening? Exactly. So that's why, and you can actually smell it a little bit, that's why we don't typically want to use these anymore. You lose that surface area, it's not helping you know that you have that surface area, and it can cause that type of burning to happen. Does that make sense to everybody? Okay? So what we have now are pads that are called return electrode contact quality monitoring. These are what we also call dual foil pads or split foil pads. If you look closely at this, there's two of them that are separate. What's happening with this is when it's in contact with the patient, the generator or ESU interrogates this pad and determines its level of resistance, okay? And it's looking for all the surface area. It continues to interrogate the pad, and when there's less surface area attached, it will give you an alarm. So if that happens, let's say this partially falls off, what do you typically do? What's the right way to handle that? Put a brand new pad on? That is the perfect answer. What happens if I just unplug it and plug it back in? What's happening? What's that? So let's figure out what's going on. Let's see if I can get this to work. So I'm gonna put this on my arm. This is gonna hurt.
What? Because he's hearing me.
So is it green? Okay, ready? It's gonna hurt. An alarm? What'd it do?
Registered that.
So what happened? Why is it green? I have half of this pad off my arm. Is that a problem? Right? What it's doing is, remember, it interrogates the pad for its surface area. When you unplug it and plug it back in, you have reset the surface area. It now thinks what is left on my arm is the complete surface area of the pad. Again, remember, high current concentration to a dispersive area. I have now less surface area. Is this a potential electrosurgical safety problem for your patient? Absolutely. If I continue to pull this, it'll alarm again, right? At some point, it would stop. It should stop. And it did, which is good. But you can see in that first instance, this is why your answer is absolutely correct. Ouch. You get rid of it and go on from there. Any questions on that?
If your patient's covered in tattoos and you have to place it over one, what are the risks associated with that?
Great question. So what are tattoos technically?
Scar tissue.
Scar tissue. Why don't you put a Bovie pad, a return pad over an implant?
Impedance.
Is it the
Non-conductive.
implant?
It's non-conductive.
It's the scar tissue. So the same thing, if you have tattoos, you want to avoid them. Tattoos are scar tissue. If they're older tattoos, I believe they might have metallic substance in it, right? Okay, so you should avoid tattoos. Is that harder and harder? It's, to me, I see sleeves and, it seems like everybody has tattoos, but tattoos are a concern. But it's scar tissue, and for the same reason, and that's a great question, that's why we don't put it, it's not the implant, it is the scar tissue over the implant. It's a denser, more resistive tissue, and remember, electricity has to complete a circuit, and it takes the path of least resistance. It's gonna flow around that and cause some issues, okay? Thank you for that question. So let's talk a little bit about orientation of pad, because that's important as well. What you see here is an example of edge effect burn. There's two types of pads. Hopefully you have ones here that are more square in shape, where each side has similar length. This is a rectangular pad. If I'm operating here on the shoulder, do I want to orientate this pad this way or this way? The second way. Why?
Because you get more surface area.
You get more surface area. What you see here is an example of an improperly placed pad. Key concept: electricity takes the path of least resistance. The pathway here is to that edge. That's the pathway it wants to take. That's the shortest path. And because of that, you do get some thermal edge effect on that pad. So the idea is to disperse it out along the length of it. So one of the advancements that have been made is instead of rectangular pads, there are some square ones that help with that. But when you're placing these, think about where the operative site is and ensure that you position this in a correct manner to have a lawn side towards that surgical site. Does that make sense? Okay. Single-use pad should be placed further away from the surgical site. True or false? False, exactly. So now let's talk about reusable capacitive pads. So with single foil and dual foil, those pads have electricity flowing into that pad, as was demonstrated by the grapefruit, and to the ESU with alternate current back and forth, okay? Does anyone know how these capacitive pads work? Anyone want to hazard a guess?
In their conductive gel.
Excuse me?
Isn't there a conductive gel within?
There's a insulator there. Who has one of these? Why does the touch screen work? The touch screen works because of capacitance. You have charge in your body. This is a glass screen, and on the other side there's a capacitor too. When I touch this screen, I infer charge from me through that insulator to the capacitor on the other side. That is the magic of how these things work. You have charge in your body. This is using charge in your body through a glass insulator to cause a reaction on the screen. Similarly, that's how our capacitive pads work. The big electrosurgical safety consideration with that is any electricity passing through the pad into the patient in that scenario. In other words, when I touch that screen, is electric charge actually passing from my finger? Do I get shocked at all when I touch that screen? The answer is no. It's an inferred pathway, and these infer electricity as well. So when I hook this up, Brian, can you move the orange? Yeah. much contact do I have? So, you guys can't see that. Good. Good. How much surface area did I have there? Not a lot. So what's happening is, do I have electricity going through me into the pad? I don't. Remember, high current concentration, right? I just have a couple fingers here. Again, there's nothing passing through me into this pad. It's simply being inferred through an insulator. So when Ryan hits that, I'm gonna just do one finger. Go ahead. You get electrosurgical effect, and I'm inferring current through my finger to the other side of that pad. Okay? So there's incredible safety considerations there. Would this be a no-no? What do you think? Is that a bad idea?
It looks pretty bad.
Is that a bad idea? They're not done here.
We had regular patients that have to-
Oh my god.
Is there any electricity going through me into these screws and through the pad? There's none, right? Again, really novel, very novel safety advancement with capacitive pads where that doesn't occur, right? The other nice thing is they're generally reusable, which reduces a considerable amount of medical waste. And can be used on a variety of patients and removes that adhesive reaction that you sometimes get too. So another thing that's happening here.
Haven't seen this in a long time.
Have you seen it before? Really?
So I had very little contact at one time, right? Just my finger. You know, what's happening there with that? Am I at 25-25?
Yeah.
Did everybody see that get less? Try again. So as the contact area is reduced, the bulb should diminish as well. As the resistance increases, it delivers less power. If that happens, you gotta turn up the power a little bit. But you still have, there's no heat buildup with me at all. So that's the concept of the reusable pad. Any questions regarding capacitance? Yes?
Does the patient have to be directly on that, or can there be like a sheet layer?
There can be a sheet layer. Now, obviously, the more sheet layers you have, the less likely there's going to be electrosurgical effect induced through the insulator and the material. So, you know, you can do it, but you don't want to put too many there.
So it's not a good idea to put a prone pad on top of that?
Prone pad like the pink pad?
No, like a big,
Correct. Yeah, exactly. Yeah. Now, there is a positioning guide that's on the pad, and you can, depending on the setup, can put a certain part of the body on the pad and then use your foam and other support materials elsewhere. That works okay too. Okay. Let's talk about that. Going the wrong way, sorry. So let's go over now waveforms, monopolar, and advanced technology, and the electrodes you use. Does everybody recognize these? What do we have on the right? What are those called?
Loops.
Loops, exactly. Electrosurgical loops. Then we have some very different tips here. Microneedle, ball coagulator. We have a standard blade here, and these are some examples of modified blades, right? And then a very big needle tip. But they all serve different purposes. For a long time, we had stainless steel tips. Stainless steel is kind of the standard. One of the drawbacks to stainless steel is this S-char buildup, right? You got to use a Brillo pad, scrape that stuff off. And when you scrape that stuff off, you scratch that stainless steel. And when you scratch stainless steel, you've now created crevices where more S-char can build up, correct? So today, there's blades that are coated with Teflon-like substances like PTFE, or even coated with silicone to help minimize sticking like that. This is an electrosurgical safety concern though. Reason you have to clean that is now resistive tissue, much like that scar tissue. And where electricity has to take that path of least resistance, it's got to get around that to complete the circuit. This is an example of waveforms. As we all know, there is cut as well as coag or coagulation. We can blend those waveforms as well. When you look at this and you see the duty cycle as well as the voltage, which one is the safer waveform?
Cut.
Cut. How come?
The voltage is less.
Exactly. Cut is actually the safer waveform. If you look at the voltage, coag is only on 6% of the time, but it is operating at a much higher voltage. Coag is on 100% of the time, but it operates at a lower voltage. It is truly a safer waveform to use. It's also the waveform that we use for bipolar instruments and your advanced bipolar instruments in surgery because of that. You get 3 types of tissue response. There is desiccation. I want you to think desiccation as simply drying out tissue of its water, vaporizing that water, and doing that. Fulguration is a little bit like a shotgun. You get some standoff and it sprays in the tissue, and then you have vaporization as well. Power settings can be based on a lot of things. What are your clinicians typically set them at? And if you were to ask them why they set them at there, why would they set them at that way? That's how they were trained, right? I have found in my experience, the ones that understand power settings typically be plastic surgeons and ENTs. And why is that? They're concerned about what? Tissue cosmesis, right? So they tend to understand. I see breast surgeons and plastic surgeons use cut a lot more, and they understand the power settings that they want to throttle it at. But does it, would the truth be every patient that you put on your table is different and probably needs a different setting? Right, yeah, but because our clinicians train the way that they did, it's usually a pretty standard setting that they use. So we talked about monopolar. Monopolar is simply, again, high current concentration to a dispersive pad with an alternate current. What's bipolar doing? So if I have high current concentration at a Bovie pencil and a pad, I am now taking those 2 tips and they're in the tines of these forceps. So think of one of those tines as the pencil and the other as the pad, and I'm bringing it there. The other thing that I'm doing is I'm using cut current and cut current only. Some of the fallbacks of it is you have, depending on your forceps, you have micro tines, you have macro tines, and forceps. You can't have high current concentration. It is critically important that your clinicians are watching effect on tissue. because they hit the gas, and until they take their foot off the gas supplying that current, it's continue to gonna deliver that energy to tissue. So because of those drawbacks, you now have advanced energy devices, what we call advanced bipolar. Some of the things that advanced bipolar instruments do is they integrate adaptive controls. There are algorithms in your generator that essentially say, this is the resistance I'm measuring in the jaws as I deliver current. When I hit this benchmark, I'm gonna provide audible feedback to the clinician and tell them I think this is sealed, and then they can take a next action. That next action generally is, a lot of these devices integrate a cutting mechanism. So if you think of like a Kleppinger, who's been around a Kleppinger before, right? So they burn, and then they gotta bring in a pair of scissors and cut. What our advanced bipolar instruments are doing, it's doing all that. It's gonna burn, it's gonna tell them when it's done, and then it's gonna allow them to cut. Because we also provide some mechanisms in the back of the handset that increase compression, we can take some pretty big vessels with most of the advanced bipolar instruments available. We can take up to typically a 7mm vessel. 7mm vessel is probably that big, so pretty stout. Ultrasonic technology is another advanced form of energy that's used in surgery. So we talked about monopolar, we talked about bipolar, we talked about advanced bipolar. All of those are using electrical current at the tissue. Ultrasonic transforms electrical current. What's happening is, this is a handpiece that is attached to a device. Electricity flows through the handpiece and hits these piezo ceramic discs. When piezo ceramic discs are hit with electricity, they get excited and vibrate. And that vibration causes longitudinal movement of a blade at the end of a stick. And that's how ultrasonic technology works. Anyone use a skill saw?